All right, hello to all my friends who are joining us via recording today. Today is March 31st. We are going to focus on the first part of our lesson number 10. So we are currently building our list of topics that we want to talk about today. So let's see. I am hearing a lot about summation. We can definitely talk about summation, excuse me. Threshold is a really important idea, so that's a good idea as well. Yeah, the idea of membrane potential. Okay, synaptic transmission and neurotransmitters. Okay, so let me get a little list for myself. We definitely want to talk about summation and threshold. Channels is a good tie-in to those kind of things. Channels, the locations, and membrane potential. Okay, so the list I have for myself, my goal for what we're going to try to talk about today is we're going to remind ourselves of what it means that neuron. We're going to talk about the different kinds of channels that we have on cells in the body. And then we're going to talk about how I open or close those channels, how I use those channels to do a process called summation. So that's kind of the goal, what we're going to do. Yeah, I had to watch that one a couple of times. Yeah, that what I will say for you guys is lesson number 10 is the one that I think is going to take the most study time from you. So I was really happy to see that a lot of you had done at least a little bit of work on it ahead of time. I think that's going to help us out for sure as we start talking about stuff. So let me start with, do me a favor, somebody underneath their picture of my meme, your little microphone, I should have just X'd it out for you. Please make sure during our session today to keep that X'd out just so that you don't have any echo from what I'm saying here. So let me go to some of our pictures here. Let's start with this picture and help me out in the chat. Can you guys tell me which page does this picture come from? Okay, I'm here on page 4. Awesome. Page 3 or page 4, somewhere in that ballpark. I'm gonna approach our discussion of potential by membrane potential by looking at this graph here. So find it in your packet. By the way, I will mention for you, I did not make you a new lecture outline when we worked through lesson number 9, but I did make you a new one for lesson number 10. Hopefully you found that when you started working on lesson number 10. So that matches pretty much perfectly to lesson number 10. It includes those questions that I told you to answer with the videos that you're watching. So yeah, that's the difference in our page number there. So page number 3 in the old packet, which matches reasonably well, not perfect. Yes, it was matched much better. Yes, because I went through and I made the lesson based off of your previous outline, made some revisions, and then I gave you the new packet for it. So going forward, when I post the lessons for you, it's going to have one that matches a lot better. So yeah, if you haven't already printed the updated number 10, go ahead and print the updated number 10. I do think it's going to be worth it for you to spend that paper. So I apologize. All right, so page number 4 of the new packet, or number 3 of the old packet. Let's go through and talk about this particular graph. If we were in class together, I would tell you that this is an underline highlight star graph, meaning that we must know this graph and we must understand this graph. And if you have started working through the packet, you will have noticed that this graph shows up like 3, 4, 5 times, a ton of times. I joke that this is my favorite graph of the entire semester because we see it all the time. So what this graph is showing me is if you look over on the left side of the graph, it has this marking over here on our y-axis called membrane potential. Now, it has been quite a while since we did unit number 1, but we did talk about this word potential way back in unit number 1. Does anyone happen to remember what I told you guys, what word to use to replace potential? It was a long time ago. Yeah, a couple of us have remembered. Absolutely. When you see that word potential, I kind of want you in your mind or even on your paper to cut off and say charge. Remember that we said that all of the cells in your body are polarized cells. Polarized means that the charge on the inside is not the same as the charge on the outside. So what this graph is showing me is the membrane potential or the membrane charge. And so I added a couple of little cartoons to our graph here. So we start off here at rest. And again, remember back to unit 1, we actually talked about what we called the resting membrane potential. That's what I've got going on over here. So when we're talking about a neuron, or even when we're talking about a muscle cell, because here's a little wink wink nudge nudge for you, that neurons and muscle cells, they are very similar in the way that they work. So muscle cells have a resting membrane potential, meaning a charge on their membrane when they're not contracting. Neurons also have a resting membrane potential. This is their charge when they're not receiving any messages. So when I look at this graph starts with a neuron that's not getting any messages. And then notice the next place on my graph is called stimulus applied. Maybe a word for us to write under stimulus or by stimulus is the word neurotransmitter, because what's going to make my neurons go through and change their membrane charge is when they receive neurotransmitters. So at the point on my graph, and I added for you a little lightning strike here, because my neurotransmitters are going to end up changing the charge or the electricity on my membrane. So when I get a stimulus, which is going to come in the form of a neurotransmitter, that's going to change my membrane charge. If we change that charge enough, here's something that we asked to talk about today, we might get to something called threshold. And threshold is a little bit what we might want to consider the point of no return. If I hit threshold, my neuron is going to talk to its neighbors. Kind of the way that we phrased our whole lesson, number 10, was the idea that neurons like to talk to each other. So they can only talk to each other when their membrane charge gets all the way up here. That's why we got our little text bubble up here. Neurons talk to each other when their membrane charge is really high. So if a neuron hits threshold, it's going to talk to its neighbors. It's going to get all the way up to positive 30. So let's review where we've been so far. At the very beginning of my graph, we've got resting membrane potential. This is the normal charge of a neuron when it's not getting any messages. It receives a message, this stroke of lightning here, or a stimulus as the graph labels it. If that stimulus is allow me to hit this threshold value, when I hit threshold, my neuron is going to send a message. It sends a message all the way up here at the top of my graph when my charge gets all the way up to positive 30. But once it sends that message, I kind of like to think about the neuron sends the message, and then it has this moment where it realizes, oh my gosh, I'm positive 30 and I'm supposed to always be negative, like really, really negative. So as soon as it sends the message, it freaks out a little bit. Well, it freaks out a lot, actually. And it goes all the way back down toward the negative side of this graph here. It goes a little too far negative, which we can talk a little bit more about this later, but it goes a little too far negative. Ultimately, though, at the end of all of this signaling stuff, we're going to go back and get back to our resting membrane potential. So big picture, what this graph shows, like I said, my favorite graph of the semester here is going from not hearing any messages to hearing a message, and hearing that message causing me to talk to my neighbors, and then the process of getting back to my resting membrane potential. Excuse me. Let's remind ourselves, let me get a whiteboard here, because this is going to be a chapter where Dr. Ollis's favorite thing to draw on the board during class is going to be really important. So let me draw my favorite thing here. Who knows what I'm drawing? Can anyone tell already what I'm drawing here? There it is. Well, a penguin, right? I should draw a penguin. There's got to be a penguin today. Yeah, I'm drawing, so some of us said a neuron. We should draw a neuron together, actually. What I'm drawing is our salty banana. I'm going to bring back the salty banana, but you all have inspired me to do some beautiful artwork later in our lesson today. So I'll try to get our daily penguin up somewhere in our lesson today. What we're going to do right now is a salty banana. Neurons, just like every other in your body, are salty bananas. So we're going to have to use that to help us remember that we have different concentrations of ions in different. Let's start with what's going on inside my salty banana. We're just going to talk about the ion. All we care about today is the ions. So what's the ion that I have a whole bunch of in my salty banana? Who lives inside that salty banana? Yeah, I'm getting my votes here. Potassium or K. We'll do K plus, which is K equals. This is what happens when you're horizontal. Can't find your keys. There we go. K plus. So we got potassium. Inside every cell, I have more potassium than I have outside my cell. That's what's going on in my banana. Whole lot of potassium there. And on the outside of my banana, here let's do some terminology review. What is the anion that I have a whole bunch of outside my banana? The anion that I have out there. Good. We're chiming in. My anion out there is chloride. When I use that word anion, what's its charge? What does anion mean? Yeah, I got some votes coming in. It means it's a negative. Exactly. Okay, so my main anion that's outside my banana is chloride. That's half of my salt. The other half of my salt is my cation, the one with the positive charge. Who's got a positive charge out there? What's my cation? Exactly. Yep, sodium, Na, sodium, Na plus. Okay, so here is my salty banana cell. The reason that I reminded you of this is because when we start talking about changing the charges on my membrane, what's going to change the charge on my membrane is these particular ions either moving in or out of my salty banana cell. So let's make a note for ourselves here since we've got our salty banana. If I were to tell you that I open up a channel for sodium, is sodium going to go in or out when I open up a channel for sodium? Which way is sodium going? Exactly. I got a whole bunch of sodium on the outside, right? Sodium's going to come in. If I open up a channel for chloride, chloride like sodium, that's going to rush inside, right? They're both coming in. If I open up a channel for potassium, where's potassium going? Yeah, potassium's going out. Okay, potassium's going to go out. Now, with the direction that these things are moving, we should probably make a chart for ourselves because this is going to help us when we start talking about summation. We should probably make some notes for ourselves about what this is going to do to my membrane charge when these things start moving. So, I can't go back. You guys can go back in your notes though. This is a number that I should have highlighted before. It was really important. I did tell you in Unit 1 it was really important. What is the number or the value of resting membrane potential? What is resting membrane? There we go. Yep, I got some votes coming in. Resting membrane potential. This is a number you absolutely must know. Underline, highlight, star, we got to know it. 70 millivolts. We've got to know that normally inside my cell it is -70, or it's much more negative inside, -70 on the inside. So underline, highlight, star, we got to know that number. That one's real important for us. I promise you that's going to show up on your exam. Is that just for neurons? It is for most of the cells in the body. The exception to -70 is actually our muscle cells. And I didn't emphasize it a lot, but I did mention it with lesson number 9. Does anyone happen to know the resting membrane potential of a muscle cell? Did anyone catch that? Yeah, some of us are chiming in. Resting membrane potential muscle is actually -90 millivolts. Oops, missed my negative. -90 millivolts. That would be another good one for us to underline, highlight, star, knowing that on a muscle cell, they're actually even more negative on the inside than most of the rest of the cells in your body. So the question was, is negative 70 just for neurons? No, it's not just for neurons. That's the number for most cells. Our exception are the muscles that we learned about last unit. They actually start a little bit lower. So the only kind of cells that we're going to talk about that change their membrane charge are the neurons, which have a resting membrane potential of negative 70, and the muscle cells that have the resting membrane potential of negative 90. So remember, this potential word just means charge, and the negative means that inside is going to be more of a negative charge than outside. All right, so I'm going to put inside my little banana here just so that we have it. In normal conditions, we are at negative 70 millivolts inside here. That's where I normally start. When I get messages from my neighboring neurons, those messages are going to come in the form of neurotransmitters. Reminder for us that a neurotransmitter is a type of chemical. What we're doing right now on our picture, but that's going to matter more when we start talking about the types of channels that are involved in the signaling process. Yes, so we're going to make a chart, like Kylie mentioned. We're going to make a chart here about what happens to membrane potential when because what gives me this difference in charge inside versus outside, what gives me resting membrane potential, is the difference in these ions. So we are negative 70 on the inside when I have my potassium that's concentrated on the inside, when I have that chloride and that sodium concentrated on the outside. When we see that part on our graph that says stimulus applied, that stimulus is a neurotransmitter. It is a chemical. It's going to allow me to move some of these ions that we see on the inside or the outside of my neurons. And we already outlined which ways are going to be moving when we open up the channels for them. So now we need to go through and see what kind of effect that's going to have on my resting membrane potential. So here's the chart that I think we should make for ourselves. Let me try to draw. Let's see if I can draw this over here. So on our chart, we're going to have a space, two spaces here. I'm going to not try to write words because that's going to be just terrible. Okay, the first part on our chart is going to be our ion, the name of our ion, and we've already outlined those ions there. Then we're going to have a space that's for the direction that they move, which we already put on our picture, but we're going to have a space for the direction. And then we're going to have a space that's basically the effect, what it's going to do to the membrane charge. So we've already said the names of all of our ions. We've got our sodium ion. We have our chloride ion. We have our potassium ion. Whenever we're talking about neurons signaling and neurons changing their membrane charge, these are the only three ions that we care about. These are the only three that are going to make stuff happen. So you guys already told me this. We have sodium, as we can see in our picture. Which direction did we say sodium was going again? Was that going in or out? Which way does sodium go? Yep, we're chiming in. We can see from our picture our arrow is pointing into the cell. Sodium is going to move in. Remember, when we're talking about the way that things move, we are talking about passive transport. So things always go from high concentration to low concentration. So sodium is going to move into my cell if I open up a way for it to move. Same thing with chloride. Chloride's going into my cell as well. What did we say was happening with potassium, though? Where's potassium going? Is that going in? Yeah, like you guys are telling me. Potassium is my one here from our list that's going out. Potassium's going out. All right, so we've got three ions that we care about. Two of them are moving in, sodium and chloride. One of them is moving out, that's potassium. The last column on our table is going to do to our resting membrane potential. Remember, when nothing's moving, my neuron is up at -70, but when things start moving, that changes that membrane charge. So our last column is basically, we're going to say, is that going to make my membrane more positive, or is that going to make it more negative? And what I'll tell you with this effect thing, we are always, what we care about always is what's happening inside the neuron. I don't care what's happening outside the neuron. So even for my things that move outside, I don't care that they're going, what's going to happen to this value that I have here on the inside of my membrane. So always consider, when we're talking about the effect, my last column over here, the only place we're really looking at is what's going on inside my neuron. So let's start here. We'll just work our way down the chart. We said that sodium is coming inside my neuron. Sodium, as we have listed here, what kind of charge? Is sodium going to be a cation, or is it an anion? Yep, there we go. Positive. Yep, we're a plus. It's a cation. Absolutely. Hey, fun stories about cats. Somehow last night we managed to leave our garage door open, and somehow we to leave the house door to our garage door open, and yet this morning I still have a cat. So fun fact, my cat did not run away in the night, which is good. But yeah, you're all typing in cats. I'm like, I gotta share a cat story. So I do still have a cat. Do you guys remember my cat's name? Let's see how many of us remember. Those were simpler times, right? Yep, Addie for short. Phi means the next one, Carrie. That's the one I gotta get next. Yep, yep, there we go. Angelica got it. The full name of my cat is Adenine. So I do still have Adenine in my house. I don't have to go out and frantically get thiamine right now. I do still have an Adenine. So we're good. Yeah, Adenine when she's in trouble. Addie for short most of the time. Most of the time she's just at it. Man, if she had run away last night. Okay, so we all got sidetracked there, or Dr. Allis got sidetracked there. I missed you, man. So like I have to share my life story with you about my cat. So, all right, you guys all told me you get a dog. There we go. My daughter would love to have a dog named Guanine. Yep. So I'm tired of confinement. Yep. I got to get all the pets and just name them all the base pairs. I at least need 5, right? Because there's the 5 bases. So we have, and then thymine the next cat. We could do guanine and cytosine dogs. Although I guess I technically have some fish that live upstairs that probably don't have a name. So maybe I could name those some things too. So, yep, uracil. I still think that uracil would make a good name for like a really grumpy cat. Like Yuri for short. Like I just picture like a really like the grumpy cat that used to be in all the memes. That he looks like a Yuri cat. So, yes, grumpy cats for sure. So, okay, now that I've thoroughly wasted our time, right? Here, I'll make this worthwhile. Our effect, we're gonna say, remember, we're gonna say to remind us how we got on a bunny trail that sodium is a cation, and that cation is we said going into my cell. When a cation with its positive charge goes into my cell, that's going to make the inside of my cell more. It's positive with it. So where we started at our -70, let me get my pointer, where I started at -70, if I let this cation of sodium inside my cell, I'm going to go from -70 to -69 to -68. I'm bringing in something that has a bunch of positive charges. So the overall effect this is going to have on my membrane charge is it's going to make it more positive. That's what happens. Open up a channel for sodium. So the first thing I can move inside is I can move inside sodium. It wants to come in because there's a bunch outside and not a lot inside. It's going to bring its positive charge with it. It's going to make the inside more positive. So along those same lines then, we said that chloride is going to move in as well. What's going to happen to my resting membrane potential when chloride moves inside? What's going to be the effect on my charge if I bring in chloride? We said chloride's gonna come in as well. Yes, I got a few votes. The way that I would approach this question is I'm going to look here at chloride. Chloride, we said, was an example of an anion, meaning it has a negative charge. So chloride, when it comes in, because it is an anion, we'll remind ourselves of that word there, because chloride is an anion, when it comes inside, it's going to make the inside of the cell more negative. We bring in this negatively charged ion, and it brings its negativity with it, which means the inside gets more negative. So when chloride comes into the cell starts at -70, and then we bring in some chloride and it goes to -71. And then it goes to -72, 73, etc. It's always going to get more negative when chloride comes inside. Where things get a little bit tricky is when we start talking about potassium, because potassium was an ion that we said went out of my cell. So when potassium goes out of my cell, it's going to take its charge with it. Potassium is another example of a cation. Potassium is a positive. When I start spitting out positives, let's see if we can take a guess here. If I start spitting out positives, is that going to make the inside of my cell more positive or more negative when I'm spitting out these positives? Awesome. Good. I'm getting a lot of votes. If I start spitting out positives, basically what I'm doing is subtraction. So I end up spitting out a cation, or I'm subtracting my positives. When I spit out potassiums, when I take away those positives, I become more negative on the inside. So when I'm spitting out potassiums, I get more negative on the inside. Oop, give my pointer back here. When I'm spitting out potassiums, we're going to get more negative on the inside. Go down to -71, -72, etc. When I bring in more negatives, that more negative. When I bring in more positives, that makes the inside more positive. So big picture, something we want to know, this table that we made here with our salty banana, this would be an underline highlight star table. We want to know who lives where, whether they live on the outside or the inside. We want to know if they're moving in or out. And we want to know what's going to happen to the membrane charge when we move that way. Are they going to make it more negative? They're going to make it more positive? What's going to happen to my membrane charge? So let me look at my questions here. I got some questions. So Parker asked, jumping a little bit ahead, which is totally fine because this will get us to where we're going today. We are at rest, and yes, we're at negative sodium in. That's what gets us all the way up to +30. Now, to get us back down to normal, we will actually use down to -70, but it's absolutely right. I rush in a bunch of sodium, and we'll talk about how we do that. I rush in my sodium, get all the way up to +30, then I freak out. Oh my gosh, I shouldn't be positive. I spit out a bunch of potassium to get me back down to -70. So big picture, yes, sodium goes out, and that's going to allow me to do that graph that we looked at before. Isabella is asking us about our types of channels. Yeah, so we should review our channels. That's something that we kind of mentioned we wanted to talk about. So our segue into talking about channels is the little hint I gave you guys over here, that neurotransmitters are chemicals. So when I am talking about the ability to bring in or spit out all of these types of ions, at the beginning, when we're talking about a process called summation, or when we're trying to get to my threshold value, let me go back to my graph here. Threshold value was that special dotted line that we saw right here. Threshold value is going to be a turning point for me because this is when I switch from one type of gated channel to another type of gated channel. So the picture that we just drew with our salty banana cell, we were looking at this part here at rest, or we were looking here at the very end at rest. all of those arrows that we drew showing us the direction that sodium or potassium or chloride moved in, all of those start to apply right here. So Kylie mentioned for us the idea of chemically gated channels, and that's absolutely correct. When I send a chemical, so here I'll put the note next to our graph over here, that neurotransmitters are chemicals. And we had already kind of said, right, that the part of my graph that talks about stimulus, that's the neurotransmitters. When I receive neurotransmitters, when I get a stimulus, I'm going to open up chemically gated channels. And those chemically gated channels can either let in sodium, like we just talked about. They can let in chloride, like we just talked about, or they can let out potassium. So neurotransmitters, the way that I can send different messages to different neurons in the body, it really comes down to which of these particular ions I am using, or I am opening, which of these channels I'm opening up to send a message. Let me peek back at Kylie's question really fast. So everything after threshold is going to be voltage gated. Yeah, so there's kind of the big picture for us here. So the reason we care so much about threshold, the reason threshold is a must know here. Let's make a note for ourselves. The voltage on threshold, what's the number on threshold? Can we tell from our graph? What's the threshold value of a neuron? Absolutely. Awesome. Yep. So negative 55 millivolts. That's my value, on my threshold value. Muscles are a little bit different. I don't believe it's negative 55 for them, and I'm not going to ask you about them. They don't do summation, so threshold isn't as big of a deal for them. So don't worry with threshold. Okay, so our numbers, by the way, that we really cared about, remember, we must know resting membrane potential, negative 70. Got to know that guy. We got to know that threshold is negative 55. And we got to know our final one up here, that the charge that I'm going to send a message at is positive 30. So up here at the very top, when I'm completely depolarized, that charge is positive 30. Those are my three numbers that I must know for this chapter here. I don't usually make you do numbers, but I'm going to make you do these numbers. Okay, so negative 70 millivolts. This is my charge when I'm resting. When I receive a neurotransmitter from a neighbor, somebody's talking to me, that are either going to make my membrane charge more positive, or it's going to make my membrane charge more negative. I listen to all the messages that I'm receiving. That's the process called summation that we'll talk about. If the sum, or when I add together all of the channels in my neuron, if that sum gets me all the way up to this threshold value, if I change all the way up to negative 55, that is going to be the point where, like a couple of us have mentioned here, at negative 55 millivolts, we open voltage gated, specifically sodium channels. Voltage gated sodium channels in particular. Let's do my favorite questions, because you know I love them so much. If it's a gated channel, it is or is not always open. A gated channel is or is not always open. Good, we're remembering. Gated means we're not always open. We got a gate, it's closed. Something is going to open that gate. In the case of a voltage gated channel, what does this voltage part mean, since it's a voltage gated channel? Yeah, we're chiming in here. When we talk about voltage, it has to do with charge. So if I'm going to open up a voltage gated sodium channel, my charge has to be wrong. And to make sure that I don't open up these voltage gated sodium channels any other time except when I need them open. That's why I have the threshold value. The threshold value is basically a neuron's way of protecting itself, because the threshold value is different enough from resting membrane potential down here at -70. If I get all the way up to -55 millivolts, that means that it must be time for my neuron to fire. It must be important enough that I should be talking to a neighbor. If my changes that come from opening up these channels do not get to threshold, this neuron will never fire. It will never send a message to its neighbors. But if my charge gets different enough from where it normally starts, those voltage-gated sodium channels will open up. So when I'm looking at my chart here, this part here that says voltage rises, where all of a sudden my charge on this neuron gets really positive really fast, that channels. Because like you guys told me, if we open up a channel for sodium, sodium rushes inside. And remember back when we were talking about our different types of channels, we said that our gated channels were kind of like a fire hose. Where they let in a ton of things really quickly. So if I open up a voltage gated sodium channel, I'm going to let in a ton of sodium really fast. That's going to get me all the way up to this +30 value, where my neuron is, here's the word you've hopefully heard or seen in videos. My neuron is completely depolarized, meaning it has the wrong charge. It went from being -70 all the way up to +30. But I've got to be all the way up at +30 because there's another type of channel that's special in neuron signaling that will only open at +30. But again, I have this moment where I realize, oh my gosh, I'm super positive. I was supposed to be super negative. Then I'm going to go through the stage called voltage falling, where I need to get back down to normal. And we talked about the way that I get back down to normal was by spitting out potassium. So voltage gated potassium channels are the ones that I'm going to use over on this downward slope of my graph. Because remember, we said if we open up a potassium channel, potassium is going to spit out. So when potassium spits out and takes its positive charges with it, that helps us to get back down to normal. We get down a little bit extra compared to normal, and we'll talk about this again eventually. But I'm going to spit out a bunch of positives because, oh my gosh, I'm +30 and I'm supposed to be -70. Spit out those positives to get me back down to normal. Let me pause for a moment and give you a chance to think. We are going to talk a lot more about what happens right here. But if you have questions about other parts of this graph, can you send them to me in the chat and I can see if we should address them with this graph or if we should address. Or if you're feeling good, send me a thumbs up. There's a thumbs up emoji for me. If you're good for now, knowing that we're coming back to that little area, shoot me a thumbs up or shoot me a question. I'll give us a chance here to type. Good, but it's a lot. Yes, it absolutely is a lot. But here's what I will say is with everything we just talked about on this graph, we kind of covered like multiple places in the packet all at once. So later in the packet, it talks about the different kinds of channels and how we open them and stuff. So we kind of jumped ahead a little bit. So a lot that we put on this one graph, but again, you'll see this graph like 3 or 4 places in your packet, and the information that we put on here applies to those places as well too. Do other voltage gated sodium channels open at number 3, voltage rises? The place where the voltage gated channels actually open is at threshold. They will stay open all the way through this part where voltage is rising. they will not close until we get all the way up here to positive 30. So the side of my graph, this whole area here that says voltage rises, all of that is because of the voltage gated sodium channels. They're open that whole time. And then we've got, so number 1 to number 3 is where chemically gated channels are open. Chemically gated channels actually open, are only used in this little section right here, right around number 2. So that probably is a good segue for us to talk about those chemically gated channels. So the chemically gated channels are involved right here, is our short answer. Carrie's asking about calcium, potassium, and sodium. I'm wondering if maybe you meant chloride. We have 3 different chemically gated channels. Calcium is involved all the way at the top of the graph. We probably won't talk about calcium today, but my voltage gated calcium channels are all the way up here at the very top. That's probably a topic for tomorrow. We'll see how much time we have today. This area that we circled, this is going to be where we see those chloride channels, those potassium channels, and those sodium channels, the chemically gated versions down here. So that's this section right here on the graph. I believe it is, yep, my next slide here. Just a friendly reminder for us of chemically gated channels. Remember that a chemically gated channel opens up with a chemical. So I've got those types of chemically gated channels that we talked about, potassium, sodium, and chloride. That's the only 3 types of channels that we open up with these chemicals here. So chemically gated channels on our graph that we were looking at are in that little section. This is what neurotransmitters do. So see how they're calling it a chemical messenger being the fancy word for a neurotransmitter here. Let me find, let's do this picture right here. Help me out on the new notes packet. What page do you guys have these pictures on? What page did these pictures come from? Okay, I'm seeing page 6. Okay, so we're about on page 6 here. Page 6 is talking to us about the 2 things that can happen when a neuron receives a neurotransmitter. So let's do some reminders here. We're seeing this word potential right here. Sorry, I tried to box and that was a terrible idea here. This word potential in these names here. Remind me in the chat, when I talk about a potential, what was the word that we traded that out for? Yeah, we trade out potential for the word charge. Okay, so in a neuron, there are 2 ways that neurotransmitters can change the charge on the membrane when they attach to a chemically gated channel. The first way they can change the charge on the membrane is what we call excitatory. One of the words that you saw as you were working on the packet is that neurons are excitable cells. Excitable cells. And when we talk about a cell being excitable, what we mean by that is that it's going to use a change in its charge, to do something. In the case of a neuron, the something that it's going to do is talk to its neighbor. So the fact that a neuron is an excitable cell means that I'm going to change my membrane charge to allow me to talk to my neighbor. So if my neurotransmitter changes my membrane charge in a way that is excitatory, like the name of this one suggests, excitatory. Excitatory means it's going to make my membrane, let's see if we can figure this out here. An excitatory positive or more negative excitatory message. Awesome. Yeah, we're all chiming in here. An excitatory message, not a lot of space over here. Excitatory message means that my membrane charge is going to go more positive. An excitatory message makes me more positive. I like that, Kylie. It's excited. It's positive. Yeah, when we're trying to figure out whether excitatory would be positive or negative, here's where that number that we were talking about before, here's where threshold is so important. Because if a neuron is going to be able to talk to its neighbor, if it's going to get all the way up to positive 30, what it actually has to do first, and realistically all it kind of has to do, is hit the threshold value. So if I get a message closer to threshold, I call that an excitatory message. Now, I do want you to underline, highlight, star, or make a note for yourself of the abbreviation EPSP. EPSP. On the exam, I will give you both the abbreviation, but also all the words, excitatory, postsynaptic, potential. But honestly, when you're studying, you don't want to have to be thinking through all of those big long words, right? You just want to be rattling off EPSP. So EPSP, this is a change in the membrane charge that is excitatory, or it's a change that makes my charge more positive. And you can see that in our little picture right here. So here's my stimulus. That's my neurotransmitter. It came in and it bound. So my neurotransmitter came in and bound here. It opened up a channel that made my membrane charge go more positive. If my membrane charge goes up, that's an EPSP, excitatory postsynaptic potential. Okay, here's together. So I don't have a lot of space on here. We'll do a whiteboard together and we'll draw some neurons. Because if we were in class together, we'd be drawing all the neurons. So here we go. When we talk about neurons talking to each other, we have to have more than one neuron. Oh, this is real fun. You know what makes this even more fun, guys, is remember I told you I'm horizontal today? So I'm totally like drawing with my mouse on my bed. This is real awesome, guys. So look at my beautiful neurons here. So we got 2 neurons. Yeah, way cool. They look real awesome. Here we go. Hey, if I can do this laying down on my bed, I'm just saying, like, you guys can draw these neurons and they're going to look legit. So here's my neurons here. 1 and 2. I was surprised, happy though, that none of us really asked about, I know I should have been an art professor. I missed my calling. The way I draw my neurons and the way I draw my penguins, like legit, that's what I should have done. Okay, so when neurons are talking to each other, they talk to each other at a place right here. We have a name for it. We talked about it in the lab packet, and we talked about what is this place here called? Yep, I'm getting a lot of votes in. Absolutely right. This place here, where my neurons talk to each other, is called a synapse. So the synapse is the place where one neuron talks to another neuron. When my neurons are talking to each other then, since they talk to each other at a synapse, we're going to name them based on their location relative to the synapse. So over here on the left, I have the one that is before. And over here on the right, I have the one that is after the synapse. So I know it's a big, long word. Maybe you don't even have to type the whole word here. When I'm talking about the neuron over here that is before the synapse, what do I call this guy here? Yep, there we go. Several of us are typing in here. My neuron that lives before the synapse is called presynaptic. It's kind of like if I gave you a pre-test. That's before you study any material. Presynaptic is the neuron that lives before the synapse. And my neuron over here called the, what's the word for after the synapse? Yeah, post is for after. Postsynaptic. Oops, postsynaptic. Okay, so anytime I send a message, there's always going to be a presynaptic neuron. There's always going to be a postsynaptic neuron. Their name, presynaptic or postsynaptic, has to do with their position relative to the synapse. The reason that I went back and drew the neurons, besides the fact that like I'm such an artist, right, is the fact that we just talked about things called excitatory postsynaptic postsynaptic potentials. That's awesome, Mary Beth. Cat walking across the keyboard. Love it. Okay. Excitatory postsynaptic potential. This is what we just talked about on the previous slide. When I'm talking about an excitatory postsynaptic potential, an EPSP, let me put some numbers on here. Are we talking about neuron number 1 or neuron number 2? Whose membrane charge, we're talking about an EPSP, whose membrane charge are we talking about? Ooh, we are divided. Okay, we are about 50% saying it's neuron number 1, 50% saying it's neuron number 2. When I look at the name EPSP, when I have that PS part in the middle, we said the PS part was for postsynaptic. Postsynaptic. Is number 1 or number 2 the postsynaptic? Yeah, number 2. There we go. Okay. When we talk about EPSPs, or in just a minute, we'll go back and we'll talk about IPSPs. I guess I should capital. It looks really weird. Okay. IPSPs. What you should keep in your mind is that we are focusing on neuron number 2 over here. It's always about the postsynaptic neuron. When you think about neurons in a line with each other, the presynaptic neuron and the postsynaptic neuron, they actually have different jobs. So a synapse, there we go. At the synapse, my neurons are talking to each other. At the synapse, the presynaptic neuron, neuron number 1, as I sometimes like to call it, the presynaptic neuron is the neuron that's going to bring the message to the synapse. Brings the message. The postsynaptic neuron is going to be the neuron that receives the message. The way that I know that is because the changes that we're talking about happening in the membrane of my cell that's receiving the message, those changes are called postsynaptic. So when you think about a synapse, neuron number 1, the presynaptic message to the synapse, the message is coming in the form of a special kind of chemicals. What was the name of those special chemicals that neurons use to talk to each other? Sodium is a channel that they open. Yeah, it's a big, long word. Yeah, there we go. Several of us are typing it for me. That was a long one. Neurotransmitters. The form of message that comes to the synapse that my presynaptic neuron releases is called a neurotransmitter. So when you think about neurons talking to each other, the presynaptic neuron, their one job at the synapse here is to bring the neurotransmitters or to release the neurotransmitters. That's their job. Neuron number 2, the postsynaptic neuron, their job is to receive those neurotransmitters. When they receive those neurotransmitters, they are attaching to, as we mentioned before, they're attaching to chemically gated ion channels. I went generic there and just called them ion channels because there are multiple ions that we can open, right? We've talked about it. Multiple different ions we're moving. We can move sodium, we can move chloride, we can move potassium. So depending on which type of chemical, which neurotransmitter this neuron spit out, that's going to dictate which kind of ion starts to rush into my cell, because each of my chemicals are the keys for different channels. So I rush in sodium or chloride or potassium. Once I rush those inside, I'm going to add them together. We'll talk about summation. Add those things together. If I hit threshold, then this neuron might go and talk to a neighbor. But big picture, when we're talking about these EPSPs or IPSPs, we're only looking at membrane charge changes that happen here in neuron number 2, in the postsynaptic neuron. If you remember from the early part in the lesson, where things start to get a little complicated or a little bit weird, is the fact that after that neuron, remember there's also a neuron down there, and this neuron is listening for any message. So this little neuron over here is listening for a message that comes from this neuron, and this neuron would send that message at another synapse. So it gets a little bit dicey when we're using the terminology presynaptic and postsynaptic. Recognize that my neurons, they typically are not just going to be one neuron talking to another. It's typically going to be this neuron talks neuron, and if this one gets excited enough, it's going to talk to this neuron. They keep going in chains. But EPSP or IPSP, we are talking about what happens in the membrane of the neuron that's receiving, or the second neuron at the synapse. Yeah, so Isabella is asking us about those IPSPs because we didn't talk a lot about those guys. Oops. Check your microphone lines for me. Let me mute you. Make sure we're crossing it off. We had a question about IPSPs. So yes, we're going to go back and look at those IPSPs. So so Mary Beth asked, so a postsynaptic neuron can be a presynaptic neuron as well. Yes, that's what that early part of the lesson was showing you guys, how we have 2 synapses in this picture, one synapse here, and we have another synapse here. So when we're talking about our first synapse, this would be the presynaptic neuron, and this is the postsynaptic neuron. Well, once we've sent our message across this synapse, now we're focusing on this synapse. And when I focus on this synapse, suddenly this would be my presynaptic neuron, and this would be the postsynaptic neuron. So absolutely, they can change what their job is. And that first part of the lesson does mention that for us. So let me go to, I'm going to go back to our picture of the EPSPs and IPSPs. Okay, so we were here. When we were here before, we were talking about excitatory postsynaptic potentials, our EPSPs. So EPSPs, we said, made the membrane charge more positive. We remember that it's positive because it's helping us to get excited, or helping us to get closer to that threshold value that would allow us to talk to our neighbor. We also, though, have those IPSPs, inhibitory postsynaptic potentials. And an inhibitory postsynaptic potential, the way I kind of like to think about those is, if over here on the left we have the EPSPs, where someone tells you a piece of hot gossip and tells you, hey, make sure you tell somebody. This is an exciting piece of news. It's kind of like over here on the right with the inhibitory postsynaptic potentials. I told you something and I said, hey, this is a secret. Don't tell anyone else about this. So the way that you would go and talk to somebody else about something is if you get to threshold. An excitatory message gets you closer to threshold, makes you want to share that message. If I tell you, hey, don't tell anybody this, if I open up a kind of channel that makes your membrane charge more negative, it's harder for you to send that message to somebody else. Your membrane charge has gone down. So an inhibitory postsynaptic potential is going to make that membrane charge get lower, makes it more negative. An excitatory postsynaptic potential makes that membrane charge more positive. It gets you closer to threshold. Excuse me. Let me check out my chat. Martha asks, so are chemically gated channels involved in both IPSPs and EPSPs? Yes. And that's a very important note for you to make for yourself. When we talk about EPSPs and IPSPs, these changes in membrane charge, This stuff, everything on the slide that we're looking at here, this is all chemically gated ion channels. Absolutely. Yes, and like Kylie mentioned, it has to be chemical because we're not at threshold yet. I have to hit threshold, that negative 55 value. I've got to get there first before voltage gated channels can open. So yeah, good note for you to write down. I'll type it up for us here. EPSPs and IPSPs are caused by opening chemically gated ion channels. That's an underline highlight star idea. EPSPs and IPSPs. These are all about chemically gated channels. Once we hit threshold, it's all voltage gated from there. We take over with voltage gated, but chemically gated channels are what generate these little changes in charge called EPSPs and IPSPs. I like Eileen's note that that inhibitory makes things lower. We're inhibiting it or we're making charge lower. Absolutely. So let me bounce to a picture that you have. Help me out here. What page is this picture from in the updated notes packet? Where did this one come from? Who can find this one for me? I may be hearing page 9, potentially. Yep, page 9. Okay. So page 9, perfect, is where we find this graph here. What I like about this graph here is this combines together for us EPSPs and IPSPs. Because here's the thing you have to recognize with neurons is getting more than one message at once. It's kind of like in real life, right? Where you very rarely get the chance to just focus on one thing that you're doing. So for neurons, their real life is, hey, we've got all kinds of messages coming in, typically from all kinds of different neurons, as you can see in my picture up here. All of these little dots that are green and red on the outside, all of these are axon terminals of different neurons. So a neuron is almost always hearing more than one message. Those messages are always opening up chemically gated channels and playing with the membrane charge of my postsynaptic neuron. So what you're seeing right here is a little bit more accurate of what happens on my action potential graph. On the graph that we were looking at before, here I'll draw the graph that we saw before. It was really nice because it was just like we had a resting membrane potential, and then we hit threshold, and we went straight up, and then we went down, and we went back, right? That's what our picture was looking like before. And so what we're looking at on this graph right here is a little more accurate of a look of what happens right here before I hit threshold. Because for most of the neurons in your body, it's not just going to be this straight shot up in this phase here. A lot of the neurons in your body are going to get a whole bunch of different messages. All of those messages is going to add together to figure out if it's going to hit threshold. So this is a more accurate representation for you of how the process of neuron signaling works. Yeah, so Parker's asking, so it's not a straight climb up. Exactly. For most of our neurons, it's usually not a straight climb up. A lot of times they are getting excitatory messages and inhibitory messages, and they got to figure out whether or not they get to do the straight climb up. So it's not usually like this, like we saw in our first graph. It's usually going to be a little bit more like this. So they have labeled for us the colors, which is really nice to show us that when I got an excitatory message, that message is highlighted in green, or the effect of that message is shown to me in green. When I got an inhibitory message, the effect of that is shown in red. Now, if we didn't have our little key over here to guide us in what these colors meant, we could figure that out from picture. So let's go through and look at this picture together. I start over here on the left at resting membrane potential. Pilar asked about yellow. Yellow is just on charge. It's kind of when it's normal, if you will. So I start off with yellow where there's no real ions that are here at resting membrane potential were normal. I got my first message right here. So the first message that I got right here made my membrane charge go up. I went positive. So this first message that I received that opened a chemically gated channel over here, that made my membrane charge get higher. That means that the first message that I received was an excitatory message. It made my membrane charge higher. But it did not make my membrane charge, it didn't open up enough to get me all the way up to negative 55. So I have not hit threshold yet after this message. I'm not going to do anything about the fact that I got an excitatory message. Nothing happened. I got another message that made my membrane charge more positive. Again, that got me closer to threshold. I'm really close, but I'm not close enough to hit threshold. So again, I'm still not going to do anything. I'm still not going to talk to my neighbor. After I got my next message, notice that my next message opened up ion channels that made my membrane charge go more negative. So this next message that I got, we would consider that an inhibitory message. It led to an IPSP, a change in my charge that brought me back to normal. Or excuse me, that brought me back lower. Now notice that I have this little stage right here where it's yellow. Maybe a good note to make for yourself right here in this little stage where it's yellow. What I see happening in this little stage here, the membrane charge changed just a little bit. The way that the membrane charge changed just a little bit here is thanks to leakage channels. Thanks to leakage channels. This little place right here where I got a little bit more negative, just a little bit, that was the work of leakage channels. Now, let me ask my favorite question. Leakage channels are or are not always open? Are or are not always open? Yeah, I've got several votes. When we talk about a leakage channel, remember that leakage channels are like a leaky faucet where they're always dripping just a little bit. Leakage channels are one of the things that contribute to getting me to my resting membrane potential. They help with it. They sometimes also hurt it. But what you want to think about right now for this little line right here, this little space where membrane charge changed just a little bit, that's because I wasn't getting any messages. There's no chemically gated channels that are open right here. But because I have some leakage channels in the membrane, and because a neuron wants to be at negative 70 millivolts, it will start, it kind of basically says, well, I'm not hearing any other messages, so I guess it's time for me to go back toward normal. So this is the neuron kind of giving up on hearing any more messages from its neighbors. We use some leakage channels here that kind of just bring that membrane charge down just a little bit. But all of a sudden I get another message, and that's why we go back to having our colored changes here. So notice that this is a very slow, gradual change compared to the changes that we see with an IPSP, where it drops down and gets lower, or an EPSP, where it jumps up and gets higher. So just a little period where this neuron got no messages. It receives that next message. This is another excitatory message that makes it go a little bit more positive, still below threshold, and especially after I get that next inhibitory message, I'm still way below threshold, but all of a sudden this neuron gets a very strong excitatory message. It brings its charge all the way up to threshold, and at that point my membrane charge spikes. Remind me, the kind of channels that open up when I hit threshold, what did we call those kind of channels that open up once I hit threshold? Because I got this excitatory message. Gated, yep, so they were gated, and we are up at a higher charge. Exactly, there we go. When I hit threshold, I am opening up a voltage-gated sodium channel, in particular, voltage-gated. Yeah, no worries. Yeah, Isabella's chiming in that it's a sodium channel. That's correct. When I hit threshold, I open up my voltage-gated sodium channels. And in rushes all of that sodium for me, rushes in, brings my membrane charge all the way up to positive 30, and then we will end up rushing back down to get us back down to normal. So what this picture is showing me is the process of summation. The process of summation. Everything that I see up until I get to threshold, adding all of this stuff together, this addition process, this is showing me summation. So when a neuron uses more than one message to figure out whether or not it's going to hit threshold, when more than one type of chemically gated channel gets opened up, and I add together those effects, that's the process of summation. So Kathleen asked a good question for us, and I want us to think about this, and I'm going to pose it to the class. Kathleen's question says, how do we know that when we get to this point on our graph, when we hit threshold, how do we know that the kind of channel that we opened up there is a sodium channel and not a potassium or a chloride channel? I want to put that to the class and see if we can brainstorm some ideas together. So let me type our question up here. How do we know that it's a, I'm going to abbreviate here on you guys, voltage gated VG sodium channel, not potassium or chloride? Here's our question. All right, so I'm getting lots of options in here. Let's go through and talk about what we were thinking on this. Okay, so the first thing that somebody mentioned for us is that potassium would be leaving the cell if we opened up a voltage-gated potassium channel. Yes, that's absolutely correct, that if I opened up a voltage-gated potassium channel, potassium would leave. Remember, with potassium leaving, that when potassium, with its positive, leaves, my membrane charge, does my membrane get more negative or more positive when potassium leaves? What happens to the membrane charge when I spit out potassium? Yeah, I get more negative. So if potassium leaves, I get more negative. So if my chart is spiking up, if my membrane charge is getting much more positive, I definitely cannot spit out potassium to make my membrane charge more positive, because that's actually going to make it more negative. And somebody else mentioned for us that chloride is also going to make the membrane more negative. What direction did we say that going in or out? What way does chloride move when I open up the channels for chloride? Yeah, chloride comes in. So chloride enters. And when chloride enters, that also makes the inside more negative. So just by knowing my salty banana, I can predict that the only option I have to make the membrane more positive is sodium. The only thing I can possibly use to make my membrane charge go up is sodium. So that's going to be the same thing whether we're talking about our voltage-gated sodium channels that make the membrane charge rush up all the way up to the top. Also going to be true when we talk about our EPSPs, our excitatory postsynaptic potentials. Those small changes more positive. The only ion I can use to make my membrane charge more positive is sodium. I have to bring sodium inside. Okay, so our question was, how do we know it's sodium? Well, we know it's sodium because that's the only thing that can make it more positive. All right, let me look back at some of the other stuff that we said here. Yeah, so somebody mentioned that using the negativity of potassium. Yeah, I'll just highlight on our chart over here. Well, let me draw it right here. This side of the chart is where I'm going to use my voltage-gated potassium channels. I guess I lost that word. Here, I'll put K+ below it. Voltage-gated potassium channels, because they make things more negative, that's what I'm going to use to get back down when I'm done I like to call it freaking out my membrane charge. When I'm done freaking out my membrane charge, that's gonna be what I use to bring it back down. Yeah, and Parker just kind of summarized the same thing for us. So sodium's the only one that moves in with that's positive. Potassium can only leave. That makes it more negative. Absolutely. So great. And what I'll tell you guys too, as you're thinking about these ions, this is why we started with salty banana, because if you know that sodium and chloride both come in, and they only come in, we know that that's going to make them more positive when sodium comes in, or it's going to make it more negative when chloride comes in. And if we know potassium is always going to leave, and potassium has a positive charge, it's always going to make the cell more negative. Inside and out, if we know our salty banana, you can make predictions about which kinds of ion channels we open up when we've gotten an excitatory message or an inhibitory message. So absolutely, go back to that salty banana. That was all the way back in Unit 1 that we talked about the salty banana. That is our overarching idea with our neurons here, with their signaling. What I think I want to use the rest of our time today to talk about, we'll talk more tomorrow about this part of our graph where we're coming back down. What I want to talk a little bit more during our time today about is I want to focus on this process here with summation, because there are a couple of different types of summation that we can do. So we'll talk about those types of summation, and we'll compare them to all those text messages, right? The example that we had with text messages. So we'll use that to talk about summation. But keep in your mind, one of the big ideas that we definitely want to have gotten out of our discussion here with the EPSPs and the IPSPs. We want to know that an EPSP, an excitatory postsynaptic potential, means the charge went up. And we want to know that an inhibitory postsynaptic potential means the charge went down. We also ion channels that we opened up. Was it a chemically gated potassium channel? Was it a chemically gated chloride channel? Chemically gated sodium channel? Things with EPSPs and IPSPs. Any last minute questions about that before we talk about our two types of summation more in depth? Any more questions about EPSPs and IPSPs? Or thumbs up? Want to give me thumbs up? We're typing the word no. You give me thumbs up. One day I got a dancing emoji. That was fun. Okay. Looks like we're feeling okay about these things. Excellent. Well, if you think of questions as we move on, feel free to light up the chat with them, and we can always come back to banana. Here's why we learned it in Unit 1, right? There we go. I got that dancing emoji back. Awesome. I just got to make sure I give you guys a penguin, right? By the end of All right, let's go through and talk. Well, here, let's do this picture really fast here. There's not a lot of notes for you to really take on this picture. I mainly include it just to show you that things aren't as simple as some of the other pictures that we use in the PowerPoint show for us. So this picture shows you I've got a postsynaptic neuron. This is one postsynaptic neuron here. Hey, by the way, when I talk about postsynaptic neurons, when I say it's postsynaptic, is that neuron number 1 or neuron number 2? When we were using the terminology or those numbers, postsynaptic would be, yeah, getting a whole lot of number 2s in there. Awesome. A postsynaptic neuron, this is neuron number 2 here. What I want to highlight for you is notice all of these different neurons that are over here attached to this one. Here's some lab terminology for you from last week. Each of these little things that we see down here, all of these are the axon terminals, or sometimes they're called a synaptic knob. This one postsynaptic neuron is synapsing with, or it's talking with, all of these different presynaptic neurons here. So the picture that we looked at that showed all of those different messages making the charge go up and down, those messages were coming from all of these different neurons that we see here. So this neuron is receiving a whole bunch of different messages. Some of those messages, as you can see on their color-coded axons, are the green ones. That'd be the excitatory messages. So an excitatory message is going to tell this neuron, hey, you should really talk to your neighbor. But at the same time, the neuron also has some messages that it's receiving that are also inhibitory messages. Some of the neurons that talk to it, their one job in talking to it is telling it not to talk to another neuron. And we probably won't have time, unfortunately, during our class together this semester. But when you talk about tetanus, you know, that thing that we all get booster shots for, right? So tetanus. Tetanus is a medical condition where my neurons are constantly firing. So they're constantly sending a message to muscle cells, telling those muscle cells to fire. The problem with tetanus is actually that we end up blocking or inhibiting our inhibitory, can't spell, inhibitory neurons. So these guys here that are supposed to tell the neuron on occasion, hey, we don't want our muscle to contract right now. If these guys get blocked or they get damaged by the tetanus toxin that comes from bacteria that live in the soil, if they get damaged and they stop sending the inhibitory messages, this postsynaptic neuron might fire all the time, which would lead to muscle spasms. Yeah, Eileen's mentioning lockjaw as well. Yes. So lockjaw is an example where your jaw muscles, they're constantly contracting because we're not sending that inhibitory message. So it's very normal that neurons are getting inhibitory messages and excitatory messages. That a neuron doesn't go crazy. That's the benefit of having that threshold value, right? It basically kind of ignores all of the messages it gets, or it's at least adding them together, kind of putting them into a blender to see what comes out. If we don't hit threshold, it adds together all the messages, and the only time it's ever going to do anything is if it gets to threshold value. How sarin gas works. It's a similar problem, but it's not the same. Let me put that to the class. When you guys studied sarin gas, what was it that sarin gas directly messed with? Does anyone remember the thing that sarin gas attached to and made it not work anymore? Yeah, so I'm getting a bunch of the abbreviations, which is totally fine because it's a beast to spell. So here's what sarin gas messes with. It's called acetylcholinesterase. Even I didn't spell it right. Let's see if I can go back and add it. Acetylcholinesterase, or ACHE. Acetylcholinesterase. What was the job of acetylcholinesterase? What did that enzyme do? Does anyone remember what the job of that was? Yeah, exactly. The first part of its name tells me working on acetylcholine. So the job of acetylcholinesterase was to break down acetylcholine. If acetylcholine sticks around longer than it's supposed to, it makes us have acetylcholine pretty much forever. And every time I have acetylcholine, that makes me contract. So the way that sarin gas enzyme acetylcholinesterase, when it messes up acetylcholinesterase, any acetylcholine that I've released is going to stay around a lot longer than it's supposed to. When we talk about tetanus, what happens with tetanus is not that I don't break down the acetylcholine, it's that I actually just keep spitting out acetylcholine. Because normally my postsynaptic neuron here would get a message that says, okay, we're done contracting the jaw muscles, don't send any more acetylcholine down to the muscle. Well, if my neurons that were sending that message that said we're done releasing acetylcholine, if these guys aren't working because the tetanus toxin went inside and killed them, that's what's going to lead to tetanus, is what it's called when you have lockjaw or when muscles are completely spasmed. It's because this neuron it is releasing acetylcholine all the time. So with sarin gas, we release a normal amount of acetylcholine, but we hear it forever. With tetanus, we release too much acetylcholine. But both of them lead to the same kind of symptoms, like you identified, Parker. So that was a great correlation to make there. They're both a problem with acetylcholine, absolutely. So here's your neurons. It gives me a little more respect for the way my nervous system works when I think about all the facts, like the fact that all the neurons in my brain are all connected like this, right? They're all talking to each other all the time. And some of them are saying, the words they put on here is fire. That's what they call when a neuron goes all the way up to positive 30. Anatomists like to say that neuron is firing. So these ones up here are essentially saying, talk to your neighbors, talk to your neighbors. And these ones down here are saying, don't tell anyone this secret. So neurons are constantly adding together the messages they get from everybody to decide whether or not they're going to flip the switch, whether or not they're going to go all the way up to positive. So let's go to this one, right? Previous one. One more. Okay. It's a little small, so I'm gonna zoom in just a little bit for us here. Okay. Give me, we haven't done this, we haven't played with this one today. Underneath your picture, underneath the picture of what's on your screen, there's a person raising their hand. If you've had a chance to look at temporal summation and spatial summation already, can you raise your hand for me? I'm curious how many of us have looked at this already. Okay, not too many of us yet. So I'll give you a little preview, and then you guys can work on this to get you ready more for office hours later in the week. When we talk about neurons adding together their messages, there are two ways that we can kind of add together messages. We can add together messages that all come from one neuron. So it's possible that one neuron can talk to one presynaptic neuron, can talk to one postsynaptic neuron repeatedly. So notice on my picture here, I've got two little messages that this neuron is sending to its postsynaptic neuron here. What this postsynaptic neuron can do is it can add together both of these positive messages that it received. When it gets that first message, that makes its membrane charge go up a little bit, not enough to hit threshold, so it starts to kind of ease back down, but then it receives that second message from the same neuron. That's enough to get it over threshold, and it's going to go ahead and fire, or it's going to go ahead and send the message. So one way that a neuron can do summation, and summation just means we're adding together messages. One way that it can add together messages is all the messages came from the same presynaptic neuron. That's temporal summation. The other way that it can add together messages, though, is what we call spatial summation. And when we talk about spatial summation, we're still receiving more than one message. So see, there's one message here and there's another one here. We're still receiving more than one message, but those messages didn't come from the same presynaptic neuron. Those messages came from more than one presynaptic neuron. And to be perfectly honest, this is kind of more of a better representation of what happens in the body, that we're going to have a lot of different neurons that are all sending messages to our postsynaptic neuron here. So these messages came into my neuron at a different location or a different space on the neuron, because one synapsed over here on this dendrite and another one synapsed on the other dendrite that I see over here. If my messages come in from different places on the neuron, or in other words, from different neurons, and I add those messages together, that's called spatial summation. So when more than one neuron sends a message, that's a spatial summation. When one neuron sends multiple messages, we call that temporal summation. So either way, what ends up happening is we still go all the way up to positive 30. We still made a message, whether I received two messages at the same time. So we got this from different locations on my neuron, different neurons talked to me. That got me all the way up to positive 30. That's spatial summation. Or one neuron talked to me more than one time. That's what we call temporal summation. I know a lot of us are hearing this for the first time, so I want you to help me out in the chat. What questions do we have right now about the difference between temporal summation and spatial summation? Or as always, you can give me a thumbs up if you're feeling okay about it right now. Temporal summation and spatial summation. Ooh, better than a thumbs up. We're dancing. Well, here, let's look at this. Got a lot of thumbs up coming. I wish that I could claim credit for this analogy here with texting, but my students come up with the best analogies to learn things. So this actually came from some previous students that I had. I got a message here. So yeah, so temporal summation is one. I presume we're talking with SMS being one cell that sends a message. Spatial summation is more than one cell sending a message. Yes, absolutely. Martha asked about inhibitory. I will mention that for you. Yeah, we'll dive into that on my next slide here. So I'll come back to your question, Martha. Here's the analogy that I got from a student actually with the difference between spatial summation and temporal summation. So I don't know about you guys, but I try during our class times together, I try to put my phone on do not disturb, because otherwise I know it's going to buzz with emails and texts and all that kind of stuff the whole time that I'm talking with you. So let's say, for the sake of argument, that you put your phone on do not disturb when you came to office hours, and at the end of office hours you turn your phone back on and you see that you have 99 text messages. And I hope for your sake that you don't, because I don't know about you guys, that would stress me out so much if I had so many text messages. I get more than like 3 and I'm like cold sweat, like, oh my gosh, what's going on? So there's a couple of text messages all of a sudden. The first option for the 99 text messages is maybe all of them came from one person. Now, if all of them came from one person and they all just said, hey, that would be so annoying, right? Although if that one person was Captain Marvel, maybe we'd cut her a little bit of slack. She must have really wanted to. I'm definitely not cool enough. Oops. I think we cut out for a minute there. Are we back together again? Give me a thumbs up if you can hear me again, because at least on my end, it looked like cut out. Okay. So we could have 99 messages all from one person. That one person could be Captain Marvel. Still annoying to have 99 messages, but I guess if they're from her, it's okay. What's more likely if you have 99 messages out of the blue is probably that you were added to a group chat. In a group chat, we're getting messages from more than one person, and that's why you can get to 99 messages so quickly, because every person can toss in a message. You can say something and then have 20 messages that come back on one message that you sent. So when we're talking about adding together messages, whether it's the 99 messages in your chat or whether it is 99 messages to a neuron, there are 2 different ways that we can do it. Now, for my friends who did already do this part of the lesson, not send me an answer. For my friends who are just learning about temporal summation and spatial summation for the first time, I want you to see if you can answer this question for me. When I talk about getting 99 messages from Captain Marvel all at once, would that be an example of spatial summation or temporal summation? 99 messages all from the same person, spatial or temporal? Okay, we're a little bit split, but a lot of us are landing on my correct answer for this one would be temporal summation. Remember, with temporal summation, I am adding up messages that I receive from the same neuron over a period of time. So temporal summation is one neuron in a short period of time. Temporal summation, one neuron, short period of time. By process of elimination, it means that my group chat would be an example of spatial summation. In spatial summation, we have multiple neurons. Multiple neurons. And hey, the other reason that I really like the group chat as an example of spatial summation is the fact that you can have a group chat going with people that are all over Texas, all over the United States, all over the world. Is when I use more than one neuron to send a message. Temporal summation, it's one neuron that sends a message. Am I back now? I think I restarted. Something weird happened. Okay. Okay, so let's see. Got some questions coming in. Does spatial summation have anything to do with the period of time? It can or it cannot. So let me go. I'm going to go back to the picture we spent a lot of time on. Go back to this picture here. This picture is really showing us, because I see how I have all of these different axon terminals that I see over here. Since I have all of these different axon terminals, I'm actually synapsing with more than one neuron. This picture specifically, when we're talking about our types of summation, this one is actually showing me spatial summation. It's not that I'm receiving my messages over a particularly short period of time. I can do spatial summation over a short time or a long period of time, but in this particular example, I am looking at spatial summation, and I didn't get all of these messages all at the same time. So spatial summation, or it could be a longer period of time. The big thing to keep in mind with spatial summation is just that there is more than one neuron sending the message. So we're having messages received over different amounts of space. That's the way the video talks about spatial summation. Different places or different spaces on your neuron are all receiving messages. PLR asked, though, it could also be in a short period of time. Yes, it could. And that's what, let me go back to another one of those pictures from your packet. That's what this one shows here. So first, your packet goes through and talks about temporal summation versus spatial summation. And then it goes through and adds in, by the way, those things we were talking about, excitatory postsynaptic potentials and inhibitory postsynaptic potentials. So things that make my charge go up or go down. By the way, we can do summation with those, which is kind of, we just assumed it was that way. But notice how I'm doing spatial summation where I've got one neuron that sends me excitatory messages, one neuron that sends me inhibitory messages. At the beginning, they don't send their messages to me very close together, but at this point, they actually sent their messages at the same time. You would have messages that come in very close together, or they could come in far apart from each other. It's just the big thing with spatial summation is it's more than one neuron that's sending those messages. In temporal summation, it's always just one neuron. What other questions do we have at this point? Because I don't think I'm going to start a new topic with us since we're about out of time today. Isabella, I see your hand. If you want to go on mic, you can, or if you want to type in a question for me, either way. Okay, you can type in your unrelated question, Carrie. I may or may not answer it now. We'll see. And Isabella, if you're working on a question, I will be happy to answer that too. Pilar asks, if they cancel each other out, then nothing happens. Absolutely. That's kind of the big idea of summation. So let's go back to our graph that we spent a bunch of time on. The big idea of summation is if I do not hit threshold, it's really like nothing matters. Like I have to hit threshold or it doesn't matter at all. So if I get, so see here how we had one positive message and then we had one negative message and I basically ended up where I started. Yes, nothing's going to happen. And even if I just get a bunch of small little excitatory messages that comes slowly, even if I just get some small excitatory messages that don't get me up to threshold, even then nothing happens. So the ultimate big picture with summation is the goal of summation is to hit threshold. If I do not hit threshold, it doesn't matter. All of it's wasted. All those little messages are wasted if we don't hit threshold. Yeah, so Eileen asked, and then this is a great way to summarize all this up together. So you have to hit threshold in order for a neuron to be able to talk to its neighbor. Yes, that is the idea of summation in a nutshell. I have to hit threshold. I'm not far enough away from my normal charge to get those voltage-gated sodium channels to open. If I cannot get those voltage-gated sodium channels to open, I cannot talk to my neighbor. So, absolutely, we got to get all the way up to the top. Okay, so let me type in for Isabella really fast in case she lost audio. Refresh. Age. Let's see. I'm going to go back to Carrie's question. Okay, so Carrie's asking about the group work. I presume she is asking about Unit 3 because you're adjusting to online assignment. I'm just grading it based on who participates in that. It's not that there's a right or a wrong answer. Yeah, so for the adjusting assignment, adjusting to online assignments where I ask you about coronavirus and how it's changed your current life, if you submit your answers to that, then you're good. I'm not going to count off in your group that, oh, only 2 out of your 4 or 5 members participated. So you write in your answers for that one, and I would say you're good on that. When it comes to the Unit 3 assignment, when we start doing content-based questions, make sure that there are answers for all of the questions. So please, I know that it's frustrating if you have group members who don't participate. I promise you that group members who do not participate will not get credit for the assignment. But what I would recommend is everyone has been assigned to their Unit 3 groups. So Unit 3 is lesson number 9, all the muscle stuff that we wrapped up, on lesson number 10, the neuron stuff we're doing now, and it's lesson number 11 with the brain. So you can go into unit number 3, I think it's called study guide, or something like that. There, when you hit your main page for that assignment, you can send out an email from the main page. That's going to be your way to get in touch with all of your group members. Send out an email and try to get the ball rolling. Ideally, we want to divide up the work across everyone. That assignment is due next Wednesday night. The reason I have it due next Wednesday night is because the exam is next Wednesday. I'm going to see how our timing goes with office hours this week. It's going to open up next Wednesday. It's probably going to close next Friday. So you're going to have a period of time, because you get one shot to take it, to sit down, hopefully with no children running around with TVs on in the background, to try to find yourself a time to take that exam. So next Wednesday night is when that will be due. Yes, I would say please start an email before you even start working on unit number 3. Please start an email chain. Maybe volunteer for a few of the questions that are in there and say, hey, we got to get these divided up. What I would say is, since it's due Wednesday night, if you have group members who have not participated by like Monday night or midday Tuesday, go ahead and assign the questions to those of you that are communicating with each other. Go ahead and assign the questions that you haven't that aren't claimed at that point, Monday night or Tuesday. I will be able to tell when I go in and grade it who did and did not contribute. So I know it sucks. I know it's a little more work for you, but I specifically picked those questions in that study guide activity because I promise you it's going to benefit you to know that information. So I know it's a little more work to have to type it into the computer, but I promise it's not wasted time, because if you can answer those questions, it will help you on the exam. So please start off with an email to your group to try to get the ball rolling, assigning questions. At the end for Unit 3 and for Unit 4, we do need to have all of those questions answered, even if some of our group members don't participate. I've got a question. If someone gets this is why I put for each of those questions the author. So that's the person who originally writes it. And then there's a space for you to put the editors, so people that went in and edited things. Please do try to edit each other's work. If there's something that is wrong, you can change that. Let me try to pull up. I emailed someone about this yesterday. The place that I want you guys to actually be entering your information on those group wikis is not in the comments section, because the comments section we cannot edit. Let me get the terminology for what you need to click. So when you go into your group wiki page for unit number 3, for example, you click on that page, you want to look for the terminology that says group wiki. Let me get a whiteboard so I can type down these instructions for you. You want to click on the part that says group wiki. You're in your group. There's options for things like email. There's option for things like collaborate. That's where we are right now, by the way. So if you wanted to have like a virtual session with your group, you could actually host one of these in your group. So you go into the group wiki. Dr. Allis has made you a group wiki that has all of the questions. In the upper right of the questions list, there is a button that says, let me make sure the word's right, Edit Wiki Content. Wiki Content. If you click on this, that is going to allow you to go in and type your answers into the wiki that's already there. Plus, when you put your answers in there and you save it, when your next group member comes in, they can click the same thing, Edit Wiki Content, then they can answer the question below you. If they need to add some notes to what you typed, if they need to correct a spelling error or a content error, they can do it from there. So please, as you're working on unit number 3, please try to enter your answers this way using the Edit Wiki Content area as opposed to just the comments. I will accept the comments if you put in your work for the first assignment. I'll go through and I'll read those. But please, for unit number 3, this is the pattern that we want to use. Or this is the way that we want to go ahead and enter our answers in to allow us to help each other with that. Somebody asked, are you fixing the grade on the homework of the extension inflection? I already fixed the homework for extension inflection from last week. I got a note from another faculty member that there may be one other error I need to check. So if that is correct, I will work on getting that correct. But most of the flexion and extension issues on last week's homework are fixed. Mary Lou asked about the group assignments. Yes, there will be 2 content groups assignments. One of them for unit number 3, one of them for unit number 4. So unit number 3 is posted for you with your questions that you need to answer for that. Those are due on April 8th, next Wednesday. Pilar asked about, yes, so just the editing the wiki thing. Please do try to do the edit the wiki. If you have a group member that puts everything in the comment, if you can do me a favor, copy what they put in the comment, put their name on it. just that'll make it easier to grade. If they only put their answers down there, I can grade it in the comments too. I will not take off points because it's not in the exact right place, but it does make it easier for me for grading to get those in there. So a question is, if I don't get in touch with any of my group members, so if you haven't heard from anyone by like evening, Parker, send me an email with the names of the people in your group, and I'll try to outreach them as well. Do your best, since you've emailed and you've messaged. That's about all you can do. So if you don't hear from them, maybe send them one more email when we get closer to the weekend. But yeah, get in touch with me if you still haven't heard from them. Again, I would hate for you to have to do everything, but with unit number 3, I do promise you that if you do end up having to do everything, it will be worth your while, because that is going to help you out on the exam. Isabella asked, so the notes were correct and there was a technical issue in the assignment. That is correct, yes. For last week's homework assignment, it was keyed incorrectly. I have fixed the key. The one thing that was different, hopefully, we've all heard from GroupMe that there was an issue. What I told you guys about Sartorius was incorrect. So let me just type up really fast. Get us know. Last week in office hours, I incorrectly told you what Sartorius does. Sartorius is actually a muscle that helps to abduct, can't spell, abduct the femur. In office hours, we said that it was an adductor, and I apologize. That was a problem with a difference between the origin and the insertion of that muscle. So that's the only note that was incorrect from last week. Otherwise, what we talked about with the muscles was correct, and I did fix the answer key to reflect that. Yes, absolutely right. It's not an adductor, it's an abductor. All right, I'm going to pause my recording since I think that's about all of our content for today. But tomorrow we will pick up with mainly focusing on lab stuff. So do try to do some lab stuff today and tonight. But we can also talk a little bit more lecture, and I've got a bunch of lecture stuff for us to talk about on Thursday as well. So let me pause that recording for us. Recorded friends, we will see you again soon.